Welcome back to our discussion of topics in abstract algebra, the online edition. I'd like to discuss today, or rather continue our discussion about even and odd permutations, and I'd like to take it in the direction of some games that we can analyze using the topic of even and odd permutations. I'd like to begin by looking at a puzzle that you might be familiar with, often called the 15 puzzle. Has a nice little history to it. It's been around for a long time. You might recognize that it's just a game where you move the tiles around, get them out of order, and the idea is to after they're out of order, to put them back in order, right? Put them back in order so that one is in this position, so that 15 is in this position, so that this is blank, and so that all the numbers are consecutive from 1 to 15 here. Of course, this is not its solved state, but the idea would be to put it in its solved state. I have a larger version of this puzzle that's going to be a little bit more adaptable to our purposes. We'll see why here in a moment. Basically, it's because I'm able to actually remove the tiles from this puzzle if I wanted to. That would be considered an illegal move for the puzzle, but it will give me a little bit of flexibility and allow me to ask some questions eventually that will be of interest. So in this puzzle, let's see, I'm going to have to remove this tile in order to play the game. I want you to notice that underneath each of the tiles, I have a number, and that number corresponds to the position of the tile. So this would be the 16th position on this board, right? Underneath the 4, I have a 4. So that's keeping track of the positions of the tiles on the board. And I could describe motions, legal moves, by describing how I'm moving a tile from one position to another. So this move right here would be taking whatever tile happened to be there. Of course, it is the tile labeled 12, but that's not important right now. Whatever tile is in this position, I'm moving to this position, right? So I would describe that as a move, a transposition, in fact, that would be described as 12 goes to 16. Right? Position 12 goes to position 16, right? I could list a bunch of legal moves as a product of transpositions, right? So here I'm moving position 11 to position 12, right? Here I'm moving the tile in position 15. It happens to be tile 15, but again, that's not the important thing. It's the tile that's in position 15 moving to position 11. Right, so moving position 15 to position 11, position 14 to position 15, right, position 10 to position 14. And here, right, this is the first time this has happened so far. This might mistakenly be labeled as moving 15 to 10. That's not what it is. It's moving the tile in position 11 to position 10, right? So this is going to be 11 to 10, right? And so on. This is going to be 7. I think that's in position 7. Yep, position 7 to position 11. Position 8 to position 7. Position, what is this? Position 12 to position 8. And let's let this be position, I think this is position 16 to position 12. Let's see, yep, that was position 16. So this move is position 16 to position 12. right? So what we have here is a product of transpositions that has recorded the moves that I've made with the 15 puzzle. Let's go ahead and actually find what permutation I get. Well, this is the permutation. Let's see if we can reduce this to a more reasonable notation. So this is, let's see, what have I got? Well, the looks like the lowest number that I've got here, I'll just start with, I think 7 was the smallest number. Not that I have to start with the smallest, but I like to do that just to keep some consistency. So let's see, this entire product, this entire composition of transpositions is going to move 7 to, let's see, fixed by that, fixed. This moves 7 to 11, and then it stays there. So 7 moves to 11. 11 moves to, well, let's see, stayed fixed here. Here 11 moved to 12. And let's see, do any of these move 12? Yes, and then 12 goes to 8. So 11 moves to 8. 8, let's see, 8 stays fixed, fixed. 8 moves to 7, and then stays there. So that's going to end that cycle. Let's see, the next tile that moves, let's see, do I ever move tile 9? It doesn't look like it. It looks like tile 10 is the next tile moved. So let's see, 10 goes to, well, let's see, first it goes to 14, and then let's see, 14 stays fixed from there on out. So 10 goes to 14, 14 goes to 15 and stays there. 15 goes to 11, 11 goes to 10, stays there. So we end that cycle. Let's see, what's the next number I've not hit yet? I think 12. 12 goes to 16. Stays. And then 16 goes to 12. Ah. So it looks like 12 stays fixed. 13, let's see, do we have 13 showing up? No, but 14 does. Let's see, so 14 goes to 15, stays fixed. Oh, we already had 14. Beg your pardon. Are there any others? So it looks like, are there any numbers that do not appear? Any numbers that appear in a transposition here that do not appear down here yet? Let's see, well, 16. So 16 goes to 12, 12 goes to 11, 11 goes to 15, which goes to 14, which goes to 10, which goes to 11, which goes to 7, which goes to 8, which goes to 12, which goes to 16. So 16 also remains fixed. So it looks like I'm done here. Well, I didn't need to start a new cycle at all. And so this product of transpositions reduces to this product of, we have a couple of 3 cycles that is equal to this product of transpositions. Well, let's see how that relates to what we have in the puzzle right now. Keep in mind, whenever we began, each numbered tile was in the position of its number, right? Tile 7 was in position 7, tile 1 was in position 1, still is. All right, but what we have now, what this is telling us, is that tile 7 should now be in position 11. Well, let's look at tile 7. There it is, there's tile 7. Where is it? It is in, let me pull this out. It is in, well, position 11, sure enough. Tile 7's in position 11. Tile 11, this says it's in position 8. Well, there's tile 11, and sure enough, it is in position 4, 5, 6. It is in position 8. There it is, right? Tile 8 should be in position 7. Yes, it is. This says that tile 10 should be in position 14. There it is. Tile 14 should be in position 15. Yep, sure is. And tile 15 should be in position 10. There's tile 15 up here, and that's 8, 9, 10. That's position 10. And so that's how we can use products of transpositions. Let's just do it that way. There it is, position 10. Right, to analyze what the final position of the board is going to be. Just multiply the transpositions together that indicated the moves that we made, and we can tell what the board looks like. So another very interesting question about the 15 puzzle. Let's get this back in order again before we get going any further. There we go. I think that's in order. All right. So back in, I think it was 1880, a man named Sam Lloyd was a puzzle inventor. He did not invent this puzzle, although he claimed to, and was so successful in making that claim that whenever he died, every obituary that was written about him identified him as the inventor of this puzzle. But it was invented long before he was even born. But one thing that he did do to help to popularize the puzzle was the following. He made the following challenge, and with this particular puzzle, since I can remove tiles, I will. What he did is said, if you start with the puzzle in this unsolved state, can you figure out a sequence of moves, don't know how many, that will put it back into its solved state, right? Now that, what I just did, you're not allowed to do. That's not a legal move of the puzzle. You can only move by sliding, right? And he offered $1,000 to anyone who could solve that puzzle. Now, mind you, it's necessary in a puzzle in solved state has the 1 in position 1, has position 16 empty, and would have all the numbers in their position. So in a solved state, 14 would be in position 14, 15 would be in position 15. He offered $1,000 to anyone who come up with such a solution. Well, let's see. I wonder if we could win that $1,000 prize. Well, here's what I want you to notice. In its solved state, with that block open, let's see, that block, I've colored this block. I don't know if you've noticed, along with the 16, I have a dot, a black dot. And in, let's see, in the position above it, I have a red dot. Position next to it over here, I also have a red dot. In fact, I have this arranged so that every other dot changes red to black. So red, black, black, and then over here, red, black, and so on. And what I want you to observe is that every time I move a single tile, every time I make a transposition, I change the color, either from black to red, like I just did, or from red to black. Right? So every single transposition changes the color of the dot. But what that says is that if I'm going to move these tiles one at a time, right, one transposition at a time, I'm going to uncover a black dot every other time, right? Black dot with no moves, gonna have a black dot with 2 moves. I'm gonna have a black dot with 4 moves, and so on. But any odd number of transpositions is going to leave me with a red dot. One move leaves me with a red dot. Two moves leaves me with a red dot. So what we're asking, whenever we're asking whether or not we can take this beginning orientation with the 14 and the 15 reversed, can we get back to a state where that tile is blank, that space is blank, but these two are swapped? Well, how would I describe swapping two tiles? That would be, that's a single transposition, isn't it? I've interchanged 14 and 15. I've interchanged 14 and 15. That's a single transposition. Am I going to be able to express a single transposition, which is what? That's an odd permutation, right? It's one transposition. That's an odd permutation. Can I express that as the product of an even number of transpositions? In other words, can I express the interchanging of 14 and 15 as an odd permutation and also as an even permutation? Well, we saw in the last lesson that every permutation is either even or odd, but can't be both. So Sam Lloyd, while I doubt that he was well versed in abstract algebra, he certainly knew that it was impossible to produce a solution to the puzzle of interchanging 14 and 15 by using only legal moves and putting it back into the state with one beginning there and this being blank. It's impossible. And we can use this argument about even and odd transpositions in order to prove that. I find that fascinating. I think it's a very interesting and fun use of the notion of even and odd permutations and the fact that every permutation can either be expressed as a product of an even number of transpositions or as the product of an odd number of transpositions, but never both. Often this is called the parity of the transposition. The parity of a transposition is either even or odd, depending on whether or not the number of transpositions in which it can be written is even or odd. Another interesting puzzle that can be analyzed using even and odd transpositions, and a puzzle that might be a little bit more familiar to you, is the Rubik's Cube. I want to illustrate something with that puzzle here. So, right, of course, you're all familiar with the cube and the motions that we could make on it, right? We've talked about this in class a little bit before, right? What I want you to notice is that every motion of the Rubik's Cube, all the moves of the Rubik's Cube can be described as compositions of functions that, functions that move the locations of the cubes from various positions. So if I numbered, let's say if I numbered this cube as cube 1, that is cube 2, that is cube 3, that is cube 4, this motion of the cube, well, that could be described as the function that sends 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Isn't that what that happened, right? So cube 1 went to position 2, cube 2 went to position 3, right? Cube 3 went to position 4, and then cube 4 went to position 1. At the same time, this cube moves here, this cube moves here, this cube moves here, this cube moves here. And so if I thought of this as 5, 6, 7, and 8, then that same motion that moved 1 to 3, I'm sorry, 1 to 2, 2 to 3, 3 to 4, 4 to 1, also moves 5 to 6, 6 to 7, 7 to 8, 8 to 2, right? So I could describe this as a product of 2 4 cycles. Now you might remember that a 4 cycle is an odd permutation, and this is the product of 2 odd permutations. That's an even permutation. So whenever I'm just thinking about the positions of the individual cubes, every motion of the cube can be described as an even permutation. And so all combinations of motions of the cube can be described as even permutations. Why? Because the composition of 2 even permutations is even. That's one of the things that that you proved. Now, let me show you another Rubik's Cube. I have one over here. Right? Same cube as this one. Right? Looks rather like it's in its solved state, with one exception. Right? What I have here is a cube that, let's see, these two are certainly out of place, and it appears that this cube is the one that really belonged over here. Is that right? Yeah, this is it's a little bit hard to tell. This is an orange face. This is a red face over here. Oh, they look the same in the, right? That's the red face. This is the orange face. But let's see. So this cube is blue, orange, green, and blue, orange, green. Let's see, blue, orange, green. Blue, orange, green belongs in this position over here. So let's see. So the cube that should be over here is over there. This cube over here is the blue, green, red cube, but blue, green, red is exactly the cube that's over there. So these two cubes have been interchanged. Well, what kind of a transposition does that? I'm sorry, what kind of a permutation does that? I gave it away, didn't I? What kind of a permutation interchanges exactly 2 cubes? Well, that's going to be a transposition. And a transposition is an odd permutation. Well, if every motion of the cube can be described as an even permutation, and what I've got here is an orientation of the cube that can be described with an odd permutation, turns out this orientation of the cube is impossible. In fact, the way I put it in this was not by a sequence of moves. That would have been impossible. What I actually did is I took the cube apart. And I took the cube apart, I put it all back together again so that those 2 cubes were interchanged. So what I'm going to do after I end this video is I'm going to put it back into its original solved state by physically manipulating these guys. A little destructive, but that's what I'm going to do. Anyway, that gives us another puzzle by which we can use even and odd permutations in order to analyze the puzzle a little bit. Hope you found that interesting. Thank you for joining us, and we'll see you next time. Stay healthy. Take care. So long.